Okay, so I think the idea was to start when we can, so we can start, so I'll start. So I'm going to continue talking a little bit about one-dimensional maps. I hope to get onto the two-dimensional maps a bit later today. And so I want to start with a few definitions. When you're trying to sort of understand the mathematics of things, there are different sort of expansion properties and invariance properties that you might want to look at. So one thing is the non-wandering set. So point X is wandering if there's an open neighborhood of it such that, sorry, that should be an intersection, such that you never get back to yourself. Okay, so you wander, that should be an intersection. Maybe I'll write that down even. If there's a neighborhood U such that Fn of U intersection U is empty for all n greater than 1. Okay, so that means that, so it's a sort of sense of not recurring. So if you start somewhere at this point X and you iterate a neighborhood of it around, you never come back close to X again. Okay? And the point is non-wandering if it's not wandering. And then the non-wandering set of a map is a set of non-wandering points. So non-wandering points are ones which do come back close to themselves repeatedly. Okay. And a map, second definition, a map is locally eventually onto if for any open set U in the interval that we're looking at, there exists an n greater than or equal to 0 such that f to the n of u is a homeomorphism and the closure of f to the n u is the interval itself. So this is a really quite strong expansion property. It says that take any open neighborhood, iterate by the map, it's getting bigger and bigger and bigger and bigger, and eventually not just sorry, this slide is full of mistakes. It's a problem about not being able to right, so F is locally, let me write this down. So F, right, so I, so from the interval to itself, is locally eventually onto if for all open U contained in I, there exists an open V contained in U such that f to the n restricted to V is a homeomorphism and the closure of f to the n of V is I. Okay. So homeomorphism means that the map is monotonic. For a one-dimensional map, it basically means it's monotonic on that branch. So this means that in any open interval, there's maybe a smaller interval such that under iteration, it gets bigger and bigger and bigger and bigger, never hits the critical points, and expands out over the whole interval. So very clearly, this implies that periodic orbits are dense. Because take any x, take a neighborhood of it, okay, then that contains a V such that f to the n is a homeomorphism, expands over the whole of the interval, and in particular, contains the original interval. So by our intermediate value theorem argument from last time, there's a fixed point of f to the n, V in it, i.e. there's a periodic, so there's a fixed point of f to the n in it, and hence in particular, there's a periodic point. So in arbitrarily close to any point you choose, there is a periodic point. Okay. Right, so it also means that the non-wandering set is I, because for any interval you choose u, eventually you expand over the whole interval, okay? And that means, of course, that you expand over yourself, which means you're not wandering. Okay. So this locally eventually onto, and if you look in the literature, there are massive numbers of different sort of definitions of recurrence, coming back, and so on. So this is just one example, and I'm actually going to have one more example of definitions later. But what I want to do now is to use these examples for the tent maps. Okay, so I said last time that I was going to go through it's a principle, David and I were talking over coffee, of getting your hands dirty. Okay, it's one thing to know some principles and to sort of have some general theorems, but you want to be able to actually use these and see what's happening in particular examples. So here's a little bit of motivation of why you might want to consider tent maps in more detail. So Milner-Thurston show that every chaotic unimodal map is semi-conjugate to a symmetric tent map, TS, with slope S in 1, 2, and entropy log S. So I said that last time, and it means that in some sense, for a unimodal map, a chaotic unimodal map, the tent maps are standard models for them. They're really quite important things to do. And more than that, if the critical point, so the tent map, let's just remind you, tent map, slope S, so it's a half, 1, and 0. It has slope S here, and it has slope minus S here, and S is in 1, 2. So I'm not going to go into the entropy business here, but if the critical point here is not periodic, then the semi-conjugacy only collapses Hom-intervals. A Hom-interval is a set of points which have the same symbolic description. Okay, so if you take an interval and all points in it have the same symbolic description, that means it never crosses over the critical point. If it never crosses over the critical point, f to the n for all n is monotonic on that interval. And basically, there are two possibilities. Either that interval, or take the maximal interval with that symbolic sequence, either that interval, well, first of all, if it intersects itself, it would have to be periodic, because all points have the same interval, sorry, the same sequences. So these go into two groups. Either it means that there's a periodic orbit in there, and probably a stable one, okay, which avoids the critical point, or it's a wandering interval. So this is a technicality, okay, that if you look at the literature, well, it's quite an important technicality. If you read the literature, an awful lot of work goes into proof of the non-existence of Hom-intervals, or at least wandering intervals. Okay, because a wandering interval is an odd thing that just walks around, it never intersects itself, okay, or any of its images, and it never intersects the critical point. So it's behaving like a point, although it's an interval. And for example, in the standard unimodal quadratic family, there are no wandering intervals. Okay, but it's a technicality where, if you like, the symbolic description and the description of points under your map has an ambiguity. So if there are no wandering intervals, then if I have a point which is not periodic, okay, then, or not in the basin of attraction of a periodic orbit, then it corresponds to, there's a single symbolic sequence associated with it and a single point with that symbolic sequence. So it's about the nature of the map between the symbol sequences and the actual points on the interval. So if you like, the first thing says that if the critical point is not periodic, then actually these are very, very good models of the dynamics. On the other hand, except you might lose information about stability of periodic orbits. If it is periodic, then an interval containing the critical point can map down to a point. Okay, so you could have a situation where you have the unimodal map. Let's have some more space. Where your unimodal map is on, so let's make it the standard view x, 1 minus x. So that's a half. Critical point is at a half. Okay. So you could imagine something where the tent map 0, 1, a half, that you have an interval around here that maps under the conjugacy. Remember, the conjugacy was a change of variable, which we called h last time. It takes us from here to here, but it can map an interval to a point. It has to be monotonic, but it can have, for a semi-conjugacy, it can have flat bits. So if this is mapped to a point, well, typically what would have happen is that all the pre-images of it would also map to a point, and so you lose information about what's going on here. But you do know that this is periodic down here, which tells me that this interval goes to an interval here, an interval here. These are intervals that will map down to points, and then back in here. So what you have is a structure up here where an interval is mapped around itself. Okay. And that means that you can define an induced map in here. If you look at, here it's F3. F3 restricted to this interval is another unimodal map. It's a unimodal map because the map is monotonic here and here. It's got the critical point here. So the composition of map with critical point and two monotonic maps is a map with a critical point. Okay? So you have another unimodal map defined there. Okay. So this turns out in the needing theory approach to give you the start of a decomposition of the non-wandering set. Because basically what you're saying here is, I've got some stuff happening in here, okay, and then I've got some other stuff happening in here. Okay, so can I understand that? Well, if you think about what's happening, this is being mapped down to a point, these 3 points, and the dynamics in here, if you think about these effectively as endpoints of a Markov partition, this is giving you a Markov partition. So the red stuff here never hits the stuff that stays in there, never hits the discontinuity, and is given, you can analyze it, by the Markov partition determined by the periodic point down in the tent map, or just think of the Markov partition obtained from using the intervals here and here as your endpoints. So this starts to give you a decomposition of the non-wandering set, which says, apply this, so you take your unimodal map, it's semi-conjugate to a symmetric tent map. If the critical point is not periodic, then that tells you what is going on. If it is periodic, then you know about the red stuff because that's given by the Markov partition, given by the periodic orbit down here. You don't know about the blue stuff. But the blue stuff is determined by a new unimodal map, the induced map. So you can start again. Is that induced map, for this case it's the third iterate, is that induced map chaotic? If it's not chaotic, well, we know about non-chaotic unimodal maps. We've done that already. If it is chaotic, then it's semi-conjugate to a tent map. Right? So if that tent map has a critical point which is not periodic, then that's a good model for what's happening for the induced map, and we stop. If it is periodic, then we have this possibility that there's an interval inside the interval. I go to white, say. So there's an interval in here, which is mapped to here, maybe, and then to here, and then to here, and then back in. And this structure is repeated in here and here. And that, again, gives you a Markov partition. So at the next stage, the dynamics away from the white inside the blue is determined by a Markov partition. And, as I've drawn it here, the fourth iterate of the third iterate, restricted to this central region, is a unimodal map. It never went. So you now have an inductive decomposition of the non-wandering set into things given that are either zero entropy or given by, well, actually the zero entropy ones are dealt with here, which you have something which is determined by a Markov partition, and then the next level that you're doing. And you just keep doing that. So you have Markov partition stuff, and that's simple. We know how to describe that by a transition matrix. More stuff. And then we say, right, is that a good model for tent map? Or does that have the same process working again? If it has the same process working again, I have another Markov partition, and then I look in the induced map again, and I keep doing that. Okay? So what you do is you find that there is a possibly infinite set of Markov partitions, which are simple to understand. Okay? And at the end, you have the dynamics of the final map. And that's all coming from the kneading theory. And the reason that I'm going into this in a reasonable amount of detail is because exactly the same arguments work, slightly modified, for the piecewise smooth systems. Okay. So, we now see the tent map two things. One, the tent map is a really nice, the first sort of, if you like, level piecewise smooth system you could think of. It's continuous, but it has this non-smoothness just at this single point. So in some sense, it's one of the first piecewise smooth systems you might think of looking at. Okay. On the second level, it's fundamental to the description of the non-wandering set of a general unimodal map. Okay, so it's got two roles here, which make it, I think, an interesting thing and worthwhile to do. The other thing is that if we didn't know about the Milner-Thurston theory, and then if you cannot do theory on something like this, which is pretty much as simple as you can write down and retain some level of complexity, then it would be very hard to think of doing something more complicated. So, right, so there's a whole load of stuff, as I say, that extends this to two-branch unimodal maps. And let's not worry too much about that. But let's get on to expansion arguments. And this is again, it's trying to introduce techniques, simple things that you can do in one-dimensional case that allow you to prove stuff. So this is something that Sebastian van Strien did in his thesis. Well, that's the place where I got it from. Here's our tent map. Sx, S1 minus x. S, x, If x is less than a half, that's that increasing bit there, and the decreasing bit here. So if s is greater than 1, s is greater than 1 tells you that the image of a half is above a half. So if you like, the intersection with the diagonal is a half. It tells you that this is above here, and it tells you that you have an orientation reversing fixed point, which we sort of did last time. Okay. It also means, if you do the calculation, that the image t of a half is there, the second iterate is to the left of a half. Okay, so immediately you have t is bigger than a half, the second iterate is less than a half, and so you have a box t2 to the half, t a half, which is mapped into itself by the map. And anything that's outside this box, well, if I start down here, I walk up and I end up inside the box, as long as I'm not at 0. As long as I'm not at 1, if I'm outside the box here, I go across to here and go into the box. So apart from this point 0, which is a fixed point, which has one preimage there, but the only non-wandering point outside this box is 0. Everything else, except that one, ends up inside the box. So we want to look inside the box at what's happening in the dynamics here. Now I'm going to restrict to the interval I, which is 2 to x. So now let's take any interval u inside this interval I with length modulus of u. So I'll use the modulus sign to indicate just the standard length of an interval. Well, there's some fairly obvious things you can say. If a half is not in u, then you're either iterating under this component here with slope minus s, or you're on the left and you're iterating with something with slope s. So the length of your interval is multiplied by s. So that's what multiplying by s does. Okay? So if half is not in u, then t of u is su. And s is bigger than 1, remember. So you're expanding. You're multiplying. If half is not in u, you're expanding the length by iterating. Okay? But we're in a finite interval I. So you can't keep doing that forever. Okay? Because you know that I is invariant, so if you start within it, you stay within it, it's got finite length, and all you're doing here is you're multiplying the length by s. So at the second iterate, if you missed a half, it would be s squared, s cubed, and so on and so on. So eventually, half is contained in some iterate of u. Okay. And then what we'll do is we'll say, well, a half splits it up into two intervals, a v0 on the left and a v1 on the right. Okay, so let's draw a picture of that. So here's a half. We started with an open, I should have said open u. It mapped maybe to t of u, which was bigger, and maybe t cubed of u contains a half, and then I'm going to call that v0 and that v1. Okay. So, what do we learn? Well, this is just some proportion of t cubed of u, or tk of u, is on the left and some proportion on the right. So let's say that the length of v0 is alpha times the length of the third iterate here, whatever iterate it is, in which case the length of v1 is 1 minus alpha times that for some alpha in 0, 1. It's just saying some proportion on the left, some proportion on the right. So the proportion on the left maps down to, this is t of a half. Okay. This bit maps down to something here, t of v naught, using just Sx. So the length of v naught is just s times the length of the length of t of v naught is just s times the length of v naught, which is s times alpha, the length of tk of u. Similarly, the bit on the right is also just iterated to something, I don't know, some different color, t of v1. Okay, it's same endpoint on the right, it's t of half, but a different endpoint on the left. I don't know whether it's bigger or smaller, but it's also multiplied just by s, so it's s times 1 minus alpha tk of u. So now, if a half is not in one of these two sets, t of v naught or t of v1, then in both cases, I'm going to be applying this negative slope s bit, and I'm going to expand things by a factor of s. So the maximum of t2 of v naught and t2 of v1 is s squared times the maximum alpha, 1 minus alpha, tk of u. The maximum, that's just saying that each of these is multiplied by another s, and I take the maximum of the two, so it's s squared times the max of alpha, 1 minus alpha, times tk. Now, if you think about it, what's the max of this? Well, if alpha is less than a half, 1 minus alpha is bigger than a half. If alpha is bigger than a half, 1 minus alpha is less than a half. So in either case, the biggest of the two is bigger than or equal to a half. Okay, it's equal to a half when alpha is a half, in which case both these are the same. Okay, and otherwise it's bigger than a half. So, but it's certainly greater than or equal to half s squared. So if s squared is bigger than 2, if I take the bigger of my two intervals, it's still bigger than it was before, because I've got a factor s squared over 2 times tku. Okay. Now again, it's got to stay in a finite interval. It can't keep expanding. So eventually, what was my assumption? Well, my assumption was that a half was not in one of the second iterates of one of these two pieces where I'd come over the critical point. So that means, I hope it says here, so eventually there's an n such that you map over a half with tnu, or a component of t to the nu, which you're following in this way, and a half is in tn plus 1 of u. But now let's look at this. If I've got an interval here, containing a half, and the image of it, well, the image of it, because it contains a half, must contain this point, and the image of it also contains a half. So it actually contains the whole of this interval between a half and t a half, because it's continuous. And the image of a half t and a half is the whole interval. In other words, it's actually LEO. You can keep restricting to intervals. You see, on either v0 or v1, t is homeomorphism. It doesn't, neither of them contain this. So actually you can restrict at each stage to an interval inside u, which maps to v0 or v1, whichever is getting bigger. And every time you're doing this process, you can refine it and refine it. So you can actually get it so that there's a u1 such that t to the n and t to the n plus 1 of u restricted to u1 are homeomorphisms. They don't actually contain half as open sets, although this one will contain half as an endpoint. And you actually get an interval in here such that t to the n plus 2 v1 equals I, or actually the closure of it equals I, and so you get locally eventually onto. So this is a really simple argument, okay? All you're saying is things get bigger. And they keep getting bigger, so at some stage you've got to get over the critical point. When you get over the critical point, you get folded. But one of them's bigger than the other, or they're both the same, so follow the bigger one. That's actually bigger than we started with back there, if it doesn't contain a half again. And so you just iterate this process, and what we've proved, whoops, so what we've proved is that if s squared is greater than a half, then the attractor is the whole of this interval. Any little neighborhood blows up to the whole of that interval. So what if root 2 is less than s squared is less than 2? Okay, let's go back. Okay, our condition was s squared is greater than 2, so what happens if s squared is less than 2? Well, let's consider the case root 2 is less than s squared less than 2. Well, I have this orientation reversing fixed point here, so I can renormalize. I can look at the second iterate, which will look something like this. And remember, I had boxes within boxes, and in this case, s squared is less than root 2. Sorry, if s squared is greater than root 2 and less than root, sorry, if s squared is less than or equal to 2, so s is less than root 2, the box is mapped into itself. Okay? So I can now think about the map restricted to one of these two invariant boxes. It's the second iterate. So its slopes are s squared and minus s squared. So now, restricted to these boxes, I've basically got this picture in there, or this picture turned over, but with s replaced by s squared. So now the argument that I've just done tells you that the map with slope s squared, the tent map with slope s squared, is transitive on this interval, or chaotic on this interval, or has this interval as the non-wandering set, the whole interval, provided s squared squared is greater than 2, which is that condition. Root 2 is less than s squared, so that's 2 is less than s to the fourth. So if root 2 is less than s squared less than or equal to 2, we can renormalize and use what we know about s squared greater than 2 to say that in this case, the non-wandering set is 0, we always have 0. P0, that's this fixed point here, okay, and I1 is the union of two intervals here and here. So it's 2 to the 1 intervals, which are disjoint unless there's a funny case when s squared equals 2, the map is transitive on the whole box. It includes P0, so these are disjoint, except in this special case when they can intersect on P0. Okay, so there's a special case there, but let's not worry too much about that. So we can now keep going, right? So if s to the 4 is between root 2 and 2, we can still look at our renormalized map for t, but then we can renormalize the renormalized map and come to the same conclusions. Basically, the non-wandering set is 0, union P0, union P1, which is a point of period 2, the orientation reversing fixed point period 2, union I2, which is a union of 4 intervals. Now, it was the 2 intervals broken into 2. And that these are disjoint unless you have equality here, in which case they intersect on P1. Okay, so and now you've got that principle, you just keep going. And by induction, you get that omega of t is 0 union, a union of points pk, which are periodic period 2 to the k. So it's, pk is a periodic orbit of period 2 to the k, and In is a union of 2 to the n intervals, disjoint unless you're at the right endpoint here, in which case they intersect on the Pn minus 1. So, again, going back to the technicalities here, I've used almost no serious mathematics at all. I've done a little bit about, look, when you map by something with slope s, you increase the size of your interval by s. And I've messed around with that a little bit. And then I've used the fact that what we did last time is if there's an orientation reversing fixed point, I can renormalize, and I've fitted those two things together. And what you get is this decomposition of the non-wandering set into the period 2 to the n's, the zero entropy stuff, and stuff that's interesting. The other thing is that a tent map only works if the slope is less than 2. Otherwise, it pops out of the box. Okay? So for any s, each time I'm s greater than 1, there is going to be a stage where s to the 2 to the n is bigger than 2. So this is always a finite number. Okay? It's a finite number that this n is finite, sorry, the n is finite except, well, finite for any s greater than 1, and as s tends to 1, it tends to an number things. And so I hope you've seen a picture like this. I think Victor showed it, or something like it. Excuse me. That if I plot x against s with 1 here and 2 here, then the type of thing that we get, so this is t of s, this is t2, sorry, t of a half, this is t2 of a half, okay, and we know that our attractor is between t of a half and t2 of a half. Okay. I'm going to pretend I'm on a logarithmic scale. Here's root 2. Okay. Now, above root 2, the attractor is an interval. Below root 2, and so this is going to be very schematic, so please don't think you may have shown this picture. Okay. Below root 2, it breaks up into 2 intervals. That was so here, the attractor is 1 interval. Okay. Our next point was the 4th root of 2. And what we find is it then breaks up, into 4 attract intervals within, so we've got 2 intervals here, and then we've got the 8th root, 2 there, and this picture keeps going. Okay, so translating it between the two, and you can see that for any s bigger than 1, there will be a 2 to the n that, sorry, a root 2 to the nth of 2 that you're bigger than. So you'll get a finite number of these bands. But the band structure and what you're finding is that in the middle of these, in here, in the gap, you've got a period 1. In this gap, you've got a period 2. In the next gap, you've got a period 4, and so on. So the structure that you're seeing by this decomposition, you see very naturally in the picture that Victor showed you. How does this, let me draw another picture over here, and let's just have a think about what we know about unimodal maps. I'm sorry, I should have prepared one of these, but I didn't. Unimodal maps, we know, we had what Victor called this beautiful picture. What did you call it? We have this period doubling picture. Beyond that, we have this mess of chaos. If you look at the mess of chaos, you'll find that although you've got period 3 sitting in here, you've got windows of periodicity, and so on. If you just blur your eyes, you'll find that there's one band here, which breaks up into 2 bands, which breaks up into 4 bands, which breaks up into 8 bands, going back in the other direction. Now, these are not, on any of these, it is not necessarily the case that the attractor is 2 to the n bands, 2 to the n intervals, because you can have these stable periodic windows. But you have a band structure of 2 to the n. And this is precisely the semi-conjugacy. The semi-conjugacy ignores the fine structure and just spots the global band structure. So what the semi-conjugacy is doing is saying, when I'm here, for example, I've basically got 2 bands. And I'm semi-conjugate to a 2-band case here. So I'm semi-conjugate to something in here. Okay. If I want to know more detail, I have to look at the detailed dynamics of that 2-band tent map and ask whether the critical point was periodic. If the critical point was not periodic, then actually I've got a nice chaotic attractor here with 2 bands. If it is periodic, then maybe I'm in a window in a window. If it's period 3, then I'd have 6 because of the doubling up. I'd be in the period 6 window, and so on. But I'd then have to look at that to understand that. So this is the beginning. Here you can see a decomposition into simple periodic orbits and something interesting at the end. But in the full picture, you have something like this, and then you repeat the whole thing. And then you repeat the whole thing again. Okay. And basically, what's the idea? The big idea here is the use of induced maps to understand the structure of the dynamics. And this is powerful both in the smooth. I've been trying to sort of work from the smooth to the non-smooth. So I'm now going to do a little bit of non-smooth. But basically, the ideas are there in the smooth case, and we can understand a lot of the structure as we see, the unimodal going over here to the tent map going over here. The big irritation is that when you start doing this with the non-smooth or piecewise smooth case, things get more complicated. Rather than just period 2 to the n, as I said last time, there are uncountably many routes to chaos in piecewise monotonic maps. But uncountably many in a controlled way. I can tell you exactly what they are, but I can't because there's uncountably many and we don't have enough time. But I can give you basically a Markov partition of dynamics, or a Markov map, on which there is a map which any path in that graph, that Markov graph, corresponds to a possible map on the boundary of chaos. Which is messy. Okay. So how do we avoid, so what I want to do a little bit now is, now that we know all the, again, the principle here is that we know the answers now. Okay, so we now know what the answers are. Are there ways of avoiding the really quite technically demanding needing theory? It's not that demanding, but sort of just using, again, elementary ideas to get somewhere with the piecewise smooth. The way I'm going to talk about things is where you have unions of, so rather than in the case of the locally eventually onto said that there was a k such that f to the ku, closure of it equals I. Okay. Here I'm saying that I'm going to allow myself to take unions of what I've done before. Okay, so rather than just look at the last iterate, I'm going to look at all the iterates I've got and ask myself whether I'm covering things. This is much weaker. I'm still covering the whole interval, but it's a much weaker sort of idea. Okay. Still implies that the non-wandering set is an interval. It's less clear about what it tells you. Well, it doesn't tell you much about chaos on its own. Okay. For example, an irrational rotation on the circle is transitive. Okay. So I'm going to use transitive to mean this, that the iterates, union of iterates over the some finite union gives you the interval. People often use transitive to say that f to the nu, given any two u and v, there's an n such that f to the nu intersection v is non-zero. Clearly, this implies that, because since this is the whole interval, it contains v, and so there is an intersection. Okay. But it is one of the issues. There are all sorts of subtleties. As soon as you get, right, so I tend not to get interested in definitions, partly because you can spend your whole life trying to work out whether this definition is exactly the same as this definition or when it's not. And that is interesting, but it's not what I'm interested in, if you see what I mean. So the whole question about definitions is a sort of one where it's much easier to say, for the purpose that I have, what's the most convenient definition to use. Right, so we have this idea of renormalization or induced maps. So now suppose that we have a piecewise smooth map, so such with two branches. So there's a C in 0,1, so on 0,1, C in 0,1, such that F is monotonic and continuous on either side of the discontinuity. Okay, so we're now going piecewise smooth. Okay. So we'll say F is renormalizable, or there exists a unique map, an induced map, if there exist positive integers n0 and n1, whose sum to be greater than 2. That means that at least one of them is bigger than 1. Okay, so n0 and n1 are not both 1, although one of them could be 1. Okay. And non-trivial intervals x1c, cx2 on each side, such that f to the nk restricted to jk is continuous and monotonic. In particular, that means that f to the j, oh, that's a bad choice, f to the r of jk does not intersect the discontinuity until at least nk. Okay. And now suppose that f to the nk jk is contained in j0 union c union j1, k is 0 to 1. Okay. This is the generalization of this picture. This interval goes here, 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 back in here. It doesn't break up. But let's try to draw the same map, the same type of picture for this. So what I'm saying is I have an interval 0,1, I have C, and I have J0 and J1. Okay. And I don't know where it goes. J1 goes to f of J1, goes to f2 of J1, and then goes to f3 of J1, which is somewhere inside this whole interval. Okay. What about J0? Well, J0, I don't know where it goes. Maybe it goes here. F of J0, then maybe it goes back here. F2 of J0. The point is that the two things, because there's a discontinuity here, these two sets, one could be sent here, one could be sent here. The way I've done it here, the blue has been sent here, the white has been sent there. They're not intersecting the way I've drawn it, although they could intersect, and so on. But the discontinuity means that I no longer have a single interval that I'm following around, but because of the discontinuity, I have to follow the two intervals separately. And in some sense, that's the end of the story. Okay? Because I now have a perfectly decent Markov partition. If I map down the white to, let's call this C again, but it's not the same C. So C approach from below is, the white is mapped to there. C approach from above, so that there's not meant to be an interval here. It's just, you're both mapping to C, but one is as approached from above, one is as approached from below, okay? Because we've got this discontinuity, you have to think about, and each branch is continuous, so it has nice limits from the left and nice limits from the right, but you have to be careful about which one you're doing. I now map this down to here, I map the white down to here, I map this down to here, and what you can see now is that down here I've got a dynamic which this point goes to there, that point goes to there, this point goes to there, and in the white I've got this goes to there, that goes to there, and I've no idea what this gives me as a Markov graph, but I've clearly got 1, 2, 3 pieces. So let's just see what they do. It might be a completely, I didn't think about this, so let's just see what the naught, K0, K1, K2. So what happens if I'm in K0? This point goes to here, this point goes to here, so I go to K1. So K0 goes to K1. If I'm in K1, this point goes down here. I now approach, oh, sorry. Let's start that again. If I'm in K0, then the left-hand point goes to C. The right-hand point is C approach from below, which actually goes all the way down the bottom. That's what I missed. You've got to choose the right image. So if I'm in K0, I'm approaching C from below, so I'm applying the white, and I'm applying the blue. So I get K1 and K2. Okay. If I'm in K1, I'm on the right here, C approach from the right, that's the blue, and the blue went first of all to here, goes to there, so I get K0 and K1. So K1 goes to itself, and K0. What about K2? K2 is away from C. This point goes down here, this point goes down here, C minus, so it goes to K0. So now you can see, oh, that's quite interesting. That wasn't a bad example just to have off the top of my head. But actually, this has quite a nice, if I start in K0, I can go here, go around here as many times as I want and back. If I start here, I can oscillate backwards and forwards as many times as I want to do. So now, basically, I mean, you just follow your fingers now. You know, if you wanted to see orbits of period 4, you could go K0, K2, K0, K1, K0. Okay, you could go K0, K1, 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 back to K0, and so on. So you just follow the arrows. You could write down the transition matrix. You could tell me, you know, I could tell you everything about that. But because of this contraction type thing, that tells me the Markov partition for what's in the complement of the images of this example. I now need to look at the detail of the map to see what the induced map here looks like, which will be another discontinuous map. But it'll be a discontinuous map that still has the property that it has two monotonic branches. Because on the left, it was monotonic, sorry, on the right, it was monotonic, then it went over here, it was monotonic, it went over here, it was monotonic, and so the image is monotonic. Here, it went to a different place, and then came back, but it's still monotonic. So this sets up exactly the same induction process that I would have, but it's more complicated. I've got a Markov partition telling me what happens in here, okay? And then I've got an induced map, which is another map. Now, depending, suppose, for example, that on the right, yes, okay. So let's suppose that the branches always had, is this possible given this? Since that goes up to, right, that's probably not possible. Suppose that the one on the right is positive slope. So we've got positive slope here. The one on the left is negative slope. Okay. Then what do I get? This is, if I'm doing the blue, I've got negative slope, so the total is so far positive slope, so I get positive slope when I get back here. Okay. If I'm here, I start with positive, I do negative, so the total is negative. And then I get back here, so it's negative. So it's positive slope, total is negative. So I get a thing that is negative on the left and positive on the right. So if you like, it is still positive, negative, but it's actually negative, positive. It swaps the order that they are. And you could have more complicated things where you got both of them to be negative, or one to be positive and one to be negative, one to be positive and one to be positive, and so on. But basically, this is the story. And I don't think I want to go that much further, except I put the thing down. But that sort of illustrates the idea behind the rest of this. We talked about that. So here's a sort of a theorem. It's actually true that this S here should be, that A should be an S. Okay. So what I've said is, if it's an expanding map, okay, then we have this nice Markov graph, and then you have a decomposition of non-modeling set into this Markov graph bit plus a remainder. And then the remainder you treat in exactly the same way. So this remainder could have a Markov graph, you need another remainder, which could have a Markov graph, you need another remainder, and so on. Okay. The reason I put this is that, and I'm not actually going to go through this proof, is that it's quite easy to prove things with expanding maps. Okay. The fact that it's true for non-expanding maps takes a lot more work. I've sort of written it down. So what I was trying to do was write down something that meant that you didn't have to know the kneading theory. Okay, so this is true in general by kneading theory. So Dan Berry's PhD thesis. But it would be nice to have a sort of explanation of this, which really just uses this idea. It generalizes this idea. Okay, and I've sort of got that, but it's actually easier to do everything. When you have strong expansion, you can get things to work much more easily. But even then, you can see it's several pages. Okay, application. So this is one for this afternoon. I hope we'll have things printed out to give you. But if we take something like this, so 1 minus 2x in xn greater than 0, that's going down like this. B plus x on the right, sorry, on the left. What can you say? Okay, I've chosen b equals a fifth. And it turns out there that that has a very simple structure, but that you can answer things in terms of the Markov partition and so on. It may even be have a renormalizable structure, you can work that out a bit later. But so that's something that we'll look at. And again, I hope that I've done enough that you can actually see, at least if you don't understand, I mean, I haven't told you the full detail of the theory, but that you can start picturing how to see the dynamics of these maps in a fairly straightforward way, and in a way that, in nice examples, this is such a one, you can actually calculate with. So, that's sort of the end of that. So I suggest that we have a 5-minute break, and then we'll change topic a little bit. In fact, I think, because Victor talked quite a lot about bifurcations, so I think I'm not going to talk about bifurcations. So the pause will allow me to load a different talk. And so 5-minute pause. And we'll start again 1 minute to 12 will be 5 minutes.